So in the previous lectures, we saw about Fourier series and how we can derive Fourier transform from Fourier series by letting the frequency value to be continuous. So in Fourier series, we had discrete frequencies for the phasors. Now we'll use the same phasors as our basis of expansion, but instead of summation, now we have integration, because now the frequencies are not discrete anymore. They are not harmonics, but they can take a continuous set of values from minus infinity to infinity. So we derived Fourier transform from Fourier series by letting the frequencies to be continuous for the phasors. So we got the Fourier transform of a continuous time aperiodic signal to be represented by this capitalized version of the signal, okay, and then it is actually a function of the frequency omega. To denote that this is the Fourier transform, we'll just add a j in front of it, so that now we have x of j omega representing basically nothing but the Fourier transform of x of t. Okay, so once again, these are the same signals, but we are just simply representing them in terms of their frequency components. So how do you get the frequency components? The frequency components are denoted by x of j omega, and you obtain that by taking the inner product with a particular phasor of a given frequency. So you just take the given signal x of t and then compute the inner product of that with the phasor. So this gives the frequency component. So when you fix a particular omega here, now let us say I fix omega value to be some 10 pi radians per second. Now what do we get here? So you can evaluate the whole integral for a fixed value of omega and you will get a number. So you will get one number here, and that number denotes the frequency component that is present in the signal x of t corresponding to the phasor with the frequency 10 pi. So you can change this frequency and then you will get different numbers, and effectively what would you get is the spectrum. So for different values of omega, you can plot what is the corresponding value that you get here, and you would get the spectrum of the signal x of t. So once again, x of t is nothing but some time domain signal, and x of j omega is just denoting the frequency components that are present inside x of t. They're not two different things, it's just the same thing but in a different representation. And x of t is basically nothing but expansion of the signal x of t in terms of the complex sinusoids or the phasors. So all we do here is the expansion in terms of e power j omega. So remember, e power j omega t are the set of bases. We're expanding in terms of that. So we have a coefficient, and the coefficient is now given by x of j omega divided by 2 pi. That is the coefficient. And now you sum them up over all possible omega values. So because omega is continuous, you have this integration from minus infinity to infinity. So this is Fourier transform, and this is the inverse Fourier transform. This has fancy names given by Fourier transform and inverse Fourier transform. Effectively, what are we doing? We are representing x of t in terms of complex sinusoids, and in order to get the coefficients, we use the Fourier transform. So that's the intuition, or that is the idea behind this entire transformation. Okay, now that we know Fourier transform, let's see the properties of the Fourier transform now. These are very similar to what we saw in Fourier series case. Now let's say we have x of t whose Fourier transform to be given by x of j omega. Then what is the Fourier transform of the conjugate of x of t? So how do we find this? So it's once again simple. All you have to do is look into this equation where you compute the Fourier transform, right? So what is the Fourier transform of x star of t? The Fourier transform of x star of t is minus infinity to infinity e power minus j omega t dt. So this is the Fourier transform of x star of t. Now you can rewrite this as integral minus infinity to infinity x of t e power j omega t dt the whole star. Now what is this term? So this term is nothing but x of minus j omega. Why is that x of minus j omega? Because what is x of j omega? It is given by this integral minus infinity to infinity x of t e power minus j omega t. Now just simply substitute in this equation, in this place, just substitute minus j omega. So if you substitute minus j omega in that equation, what would you get? X of minus j omega is equal to minus infinity to infinity x of t e power minus j omega of, there is a minus omega here, so in this case you substitute a minus, right? So this is exactly what is the equation that we have here, right? So what do we have here? So this is x star of minus j omega. So this is exactly similar to what we saw in the Fourier series case. So when you take the conjugate of the time domain signal, the corresponding Fourier transform is simply nothing but the conjugated version of the previous Fourier transform and the frequency reversed. So what happens when you take the conjugate? The negative frequencies get a sign flip, and that is exactly what is happening here also. Okay. So when you take x star of t, that is a conjugation in the time domain. The conjugation in the time domain is equivalent to the conjugation in the frequency domain and also flipping the frequency component. So whatever was the negative frequency component becomes the positive frequency component with the conjugation, okay, and vice versa. What happens to the bandwidth? The bandwidth does not change. Why does the bandwidth does not change? So if we had a spectrum which looked like this, let us say the spectrum looked like this. Now after this conjugation operation, how would the spectrum look like? Because that there is a reversal in the frequency domain, spectrum will reverse, but the length of the spectrum does not change. For this reason, there is no change in bandwidth when you take the conjugation in the time domain. Now what if we simply do a time reversal? So that is, what if we try to compute x of minus t's Fourier transform? Okay. This is basically nothing but the Fourier transform of x of minus t. How does that look like? So if you take this conjugation, so this is nothing but, once again in this particular equation, what did we have? So this is the expression that we have for x of minus j omega, and in this expression, just let us say minus t is equal to s. So all we are doing is now change a variable. So we are introducing another variable s, and then we are calling that as minus t. So what does this integral become? So when t is minus infinity, what is s? Minus of minus infinity plus infinity. When t is plus infinity, you get minus infinity. X of s, okay, e power j omega s, and dt is equal to minus ds. So you get a minus ds here, and that minus would flip the order of integration. So now this is the expression that we get when we try and change the order of integration. So when we change the order of integration, we have this expression which is exactly the same as this expression, only that the variable of integration has changed. So that does not really matter because the variable of integration anyway gets integrated out. So these two expressions are once again exactly equal, which means this integral gets evaluated to x of minus j omega itself, and that is what we have here. So if you have a signal x of t and you time reverse it and then compute the Fourier transform, The only thing that happens to the Fourier transform is that the Fourier transform is also reversed in the frequencies. So what is the intuition behind these transformations? It is very similar to what we saw in the case of Fourier series. So when there is time reversal, what happens? The time reversals result in the reversal of the direction of rotation of the phasors. So if a phasor was rotating in the clockwise direction, after time reversal it rotates in the anti-clockwise direction and vice versa. So which means if there was a component on, let's say, a frequency of omega, there was a phasor with frequency omega and it has some coefficient, let's say it had a magnitude of some 10. Now after time reversal, now this phasor starts rotating in the opposite direction, which means now the phasor corresponds to a frequency of minus omega. So now the frequency of minus omega will have this magnitude 10. In essence, what are we seeing? We are seeing this reversal in the frequency domain as well. So whatever positive frequency had, that magnitude will get shifted to the negative frequency. Whatever was the magnitude for the negative frequency, that will get shifted to the positive frequency. In other words, there is a reversal of the spectrum. So the spectrum will now reverse about the origin. Okay, so that is what we see here, and that's exactly what we saw in the case of Fourier series. What about the case of conjugation? So let us say there was a phasor e power j omega t that was present inside this x of t. When you take the conjugate of that, what do we do? So we take the conjugate of both its magnitude. So let us say it had a particular magnitude. You take the conjugate of the magnitude and you are changing the direction of its rotation. So that is what we are seeing. So you are changing the direction of rotation, which means positive frequency becomes negative frequency and the negative frequency becomes positive frequency. Not only that, not only you are changing the sign of the frequency of the phasor, but the phase of this particular phasor is also changed when you take the conjugate. Okay. So both these operations do not result in a change of bandwidth because we are not changing the frequency components. We are only shifting the frequency components from negative to positive and positive to negative. So the amount of frequency components that are present are still the same. So the bandwidth does not change. Okay. Now what if we do a time shift? Then how does it reflect in the Fourier domain or in the frequency domain? So if we are shifting in time, we need to find the Fourier transform of this signal, where we have shifted the signal by minus s amount. So Fourier transform is t minus s. We'll do the same thing, that is, we'll just replace this with another variable. Okay, so basically s is some constant. We don't know what is that constant. It's an arbitrary constant. Now we'll replace this t minus some constant with another variable of integration. Okay, so when t is minus infinity, what happens to be? Still minus infinity, because s is after all a constant. S is not infinity, it is a finite constant. Okay, so because of which the limits do not change, it remains as such. So we get x of v e power minus j omega t now is nothing but v plus s. Okay. So just use this v plus s and dv. Okay, dv is equals dt from here. So in other words, we can say that this is equals e power minus j omega s, because you can pull that out. That is only a constant with respect to v. So you can pull that out and you get this integral x of v e power minus j omega v dv. Once again, this is exactly in the same form as the Fourier transform, only that the variable of integration has changed. So that does not really matter because anyway you integrate it out. Now this is equal to e power minus j omega s x of j omega itself. So you get the same Fourier transform, only thing is there is a phase shift that is added to each and every frequency component. So you take a particular frequency component, if it is of frequency, let us say 1 pi, then the corresponding phase shift would be s times pi. if the frequency component is 10 pi, then the corresponding phase shift would be e power minus js 10 pi. So depending upon the frequency, there is a different phase shift that is added. It is not a constant phase shift for all omega, but it is a frequency dependent phase shift. And that makes sense because what we are doing in the time domain is moving something by some amount. And that s time duration corresponds to different phase values for different frequencies, right? So if I have, let us say, 1 second as my shift duration, so if there is a frequency which completes 1 cycle in 1 duration, then it corresponds to 2 pi phase for this particular frequency. But if I had, let's say, another frequency which corresponds to this much of a cycle, then it does not correspond to 2 pi, but it probably corresponds to less than pi by 2 or something around pi by 2 for this particular frequency. So the phase differs depending upon what the frequency is, and that's exactly what we are seeing here. So there is a phase shift for each and every frequency component depending upon the frequency component's value. So the frequency content itself does not change, only that there is a phase shift to each and every frequency component that is already present. So because of that, there is no change in bandwidth. Now what if we do the other way around? Now what if somebody gives you the spectrum? So I have a spectrum, something, let's say, like this, and then somehow I shifted it to the right, and then if I try to compute its equivalent time domain representation, how would that look like? Would it have any relationship to the original time domain signal? It turns out that, of course, yes, that will be related to the original time domain signal. Let us see how it is related. So now we start with the inverse Fourier transform. We want to find the inverse Fourier transform of x of j omega minus some nu. So basically what are we doing? We are shifting the frequency in the spectrum by some nu. Okay. So this corresponds to 1 by 2 pi minus infinity to infinity x of j omega minus nu e power j omega t d omega. So this is the inverse Fourier transform, right? So that's all we have written. Now we'll do the same trick. We'll just take some variable. Let us call that variable as some s, and we'll do the same replacement. So we'll define another variable, and then we'll say that that variable is equal to omega minus nu. All we are doing is just changing the variable of integration. Once again, when omega is minus infinity, s is minus infinity, and when omega is infinity, s is also infinity. So this does not change. So we have x of js e power j s plus nu t ds. Okay. By the same operation that we did before, take this e power j s t inside and e power j nu t outside, because nu is constant with respect to s. So you get e power j nu t times 1 by 2 pi integral x of j s e power j s t ds. This is exactly the inverse Fourier transform, only that the variable of integration has been changed. Everything else is the same. Anyway, that the variable gets integrated out. So the only thing that we have remaining is this is equal to x of t. So which means x of t gets multiplied with e power j nu t, and that's what we have here. So if you shift the spectrum by some amount, then what happens to the corresponding time domain? The corresponding time domain signal also only has a phase shift, just like how we had a phase shift in the spectrum when the time was shifted. When the frequency is shifted, we also have a similar effect, that in the time domain we have only a phase shift. So what does this mean? It means that, let's say you have a particular spectrum and move it to the right. It means you are increasing the frequency components. if you are increasing the frequency components, what does it mean in the time domain? In the time domain, basically it means that you also have to have the corresponding frequencies included. So how do you use the corresponding frequencies in the time domain? So you can increase the frequency in the time domain by introducing the corresponding phases or the corresponding shift in the phases. So we say that x of t, let's say, contains the phasor e power, let us say it contains the phasor of frequency 1 pi t. Okay. Now let us say I want to shift it to the right. Now how does the spectrum of this particular signal look like? So if I try to plot the spectrum of this particular signal, it has a frequency component at omega is equal to pi. Okay, so if this is 0, this is pi. At omega equals pi, there is a frequency component that is present. Now I want to shift it to the right. So if I shift it to the right, let us say I want to shift it to 2 pi or 3 pi. I want to shift this to 3 pi. So to the right I am moving it by 2 pi amount. So how can I do this? I can do this by simply multiplying this with e power j 2 pi t. So I am shifting this by some 2 pi. Okay. So if I have to shift this by 2 pi, what should I do in time domain? I just have to multiply this with the corresponding phasor, right? So the effect of these two phases adding up together is just e power j 3 pi t. So I've just added them up together, and that gives me the corresponding shift I want. So that is all we are doing here. So if I want to just have a particular phasor e power j omega t to move to the right by some new times, what we are going to do? We are just simply going to say plus nu t, right? So this moves it to the right side by nu. Okay. So which effectively gives us a multiplication by e power j nu t, and that is exactly what we are having here. So if we have to move it to the left, then we have to subtract that much frequency component, and that is as good as multiplying the signal in time domain with e power minus j nu t, and that is what we will see here. So basically, why are we getting a phase shift? It is nothing but a phasor that is actually getting multiplied. So this is not just a phase shift, but this is a phasor which basically changes the frequency components of the phasors that are present in x of t already. Okay, now what if we just scale in time? So we saw that all these operations that we saw so far, they do not change the bandwidth at all. They result at best only in a frequency reversal or just a shift of frequency or only a phase change in frequency. The bandwidth does not change as such. But what if we scale the signal in time? So we saw this earlier, right? Whenever we scale a signal in time, it either gets compressed or expanded. So if something gets expanded, then obviously the frequency component in it is also getting reduced. If something is getting compressed, the frequency component is getting increased. So this should reflect in the spectrum. Let us see if it is reflected in the spectrum. So if we are computing the Fourier transform of this time scaled signal, then this is, we are going to do the same trick. All we are going to do is just do this change of variable. We just substitute another variable and then we will get the desired result that we are looking for. So this is equal to x of ct e power minus j omega t dt. Okay. Now change the variable. Let us say v is equal to ct, then dv is equal to c times dt. So we have the limits to be exactly the same as minus infinity to plus infinity. We have x of v e power minus j omega. Here we have v divided by c, or in other words we can say omega divided by c times v, and dt is dv divided by c. Okay. What is this equal to? This is in fact nothing but 1 by c times x of j omega divided by c. Okay. So, you can just replace omega dash as omega by c, then you will just get omega dash here. Okay. And now in this case you will get back the signal that we are looking for. So, basically what have we seen here? So, we see that now if there is a compression in time domain, then there is an expansion in the frequency domain. So, if c is greater than 1, there is a compression in the time domain, right? And then if c is greater than 1 here, because you are dividing here by c, then there is an expansion in the frequency domain. So, the spectrum expands. That makes sense, because whenever something gets compressed, then there is a corresponding increase in the frequency components. So, as you can see here, there is a 1 by c term that is coming outside. So, not only is that the spectrum gets expanded or shrunk, but there is also a scaling factor to the spectrum. So, what does this mean? So, what does this do? So, the reason that we have a scaling factor intuitively here is that there is a change of density when the spectrum expands or it shrinks, but the area needs to be fixed. In other words, if our original spectrum was looking like, let's say, like this, then after scaling, we should have a spectrum which probably looks like this. So, because it got expanded in the frequency domain, its amplitude has now been reduced, so that the effective area under both these cases are exactly the same. Okay. So, the area does not change, but what changes is only the density, because the density earlier was present inside this interval. The entire frequency component was densely packed inside this interval, but now because of this time scaling, the density has been moved around or transformed to be present in a larger interval. So, the density has now changed, but then the area is fixed. Why should the area be fixed? So, there is a simple way of explaining why the area should be fixed. So, look at this inverse Fourier transform expression. So, x of t is 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. Now, just substitute t equals 0 in this. So, in this expression, when you substitute t is equal to 0, this phasor term disappears. So, we have just 1 by 2 pi x of j omega d omega. This is basically the area under the spectrum. Okay. So, the entire thing is the area under the spectrum. Now, this x of 0 is the same for x of t and x of ct for all values of c not equal to 0, right. So, the x of 0 point is the same for the time scaled signal and the original signal. So, which means that should not change no matter what the value of c is. That means the area under the spectrum should also not change. So, the value of the signal at 0 determines what is the area under the spectrum. So, that should not change no matter what is the scaling factor, and that is the reason why you see a division by c here, which will take into account the area scaling, so that the area is finally normalized no matter how much you stretch or shrink. So, if we had shrunk this spectrum, then the spectrum would have looked like this. The magnitude would have jumped up. If you had expanded it, the magnitude would come down. So, this scaling enables us to keep the area fixed. So, that is why in this case we see a 1 by c here. Okay. So, this is different from the Fourier series case. So, because the Fourier series case we did not have any kind of density or an area, because every point was discrete, we did not have this. But in this case we have a density, meaning the frequencies are packed densely together that it forms a continuous signal. So, in this case this the notion of time scaling gives us a different result in the spectrum compared to what we had in the Fourier series. And also we have this notion of frequency shifting, which we did not see in the case of Fourier series. So these are two different things that you need to keep in mind. And as usual, whenever there is a time scaling, there is a corresponding change in the bandwidth. Of course, the bandwidth either expands or shrinks. So that is also something that we need to keep in mind.